Welcome back to another session of mixed signal IC design. So in the previous lecture we were looking at flash ADC, the architecture of flash ADC and how the conversion happens in a flash ADC. We also looked at the design of 3-bit flash ADC, how the thermometer coding will be converted into digital code, and we also looked at the accuracy issues with respect to the matching of the resistor string as well as the input offset voltage of the comparator. So one thing which was very particular about flash ADC is its highest speed, because the ADC is able to give output on every clock cycle. That is one important thing. And another thing, it is not as an advantage, but still we know that the requirement of area and the power was more in the case of flash ADC. And for that reason, since the number of comparators and the power requirement for those comparators is high, generally flash ADC is limited for 8 bits of resolution or so. So that means we are in need of another architecture which we can go ahead and get higher resolution, say for example 10 bits or more than 10 bits, like 12 bits or 14 bits, that kind of. So that whenever we are in need of that kind of resolution, going ahead with flash ADC is not a apt solution because of the area requirement. So today we will look at another architecture called as pipeline ADC. Alright, so let us look at this pipeline ADC. So in contrast with this flash ADC, which was giving the digital output on every clock cycle, pipeline ADC is a little bit different from that. And pipeline ADC can be considered as an n-step converter. You will understand what is this n-step conversion when we discuss the architecture. So what happens here is there will be multiple stages for this ADC, and 1 bit will be converted per stage. So we call it as 1 bit conversion per stage. Alright, so one another advantage is we are able to achieve higher resolution at fast speed. So that is another important feature of this, able to achieve a high resolution, when you say high resolution, more than 10 bits, and comparatively fast speed at fast rate. Alright, so if you look at the architecture of this pipeline ADC, here the architecture will be having n stages. So what do you mean by n stages is, for example, if you are looking for a 3-bit ADC, it will have 3 stages. Similarly, for an n-bit ADC, you will have n such stages. Alright, so when you look at we'll slowly develop the architecture. So if you look at the architecture, you will have altogether you will have n stages depending on the number of bits of the ADC. Now for each stage, there are several blocks we include for every stage. So one is a comparator itself. So comparator, or otherwise you can think comparator is nothing but a 1-bit ADC, right? So you'll have a comparator, you will have a sample and hold circuit, you will have a summer, and also you will have a amplifier. So these are the various blocks what we use per stage. Like that you will have n such stages. Alright, so what we do is we will quickly look at the architecture of this ADC and then we will come back. Yeah, so as listed, this will be having n stages. So if you look at one stage, first of all we'll have the input signal, and the input signal will be given to a sample and hold circuit, where the input analog voltage will be sampled and held, right? So that output will be available at the output of sample and hold circuit. Now at this point we start our comparison. So this sampled output will be compared, or we use this 1-bit ADC or comparator to compare the sample data with a reference voltage. And reference voltage what we keep in this case is always we'll have a reference voltage, and this reference voltage is kept at Vref by 2. That is a standard reference voltage what we use. Now, depending on the operation, we will decide whether the minus input of the comparator should be connected to this Vref or to some other voltage. So that let us see that. So the sample and hold output is there, and then you will have a comparator, and directly comparator will give you some output. All right. So if I let me leave it like this. Now at the output of this sample and hold circuit, you will have one summer. We look at the operation summer, and one input of summer is sample and hold output itself. Then the other input of this summer is will be connected. It will be connected either to this point or towards the other point where you can see a ground terminal, right? So we'll see the operation. This is how this works, right? So the input signal, there is a sample and hold circuit, and the output of sample and hold circuit is given directly to a summer and also to the plus input of the op-amp, the comparator, and at the minus input, either it will be connected to Vref by 2 or it will be connected to Vref by 2, and the summer input, another input of summer will be connected either to this Vref by 2 or to the ground terminal, right? And output of the summer is again given to an amplifier. So amplifier is with a gain of 2. This is what we'll have. All right. So this is what in general we write. So say for example, if we are looking for an n-bit ADC, we'll have this as the MSB position, and LSB position will be on the right. So this is one stage comprises of a sample and hold circuit here, a comparator here, then a summer here, and an amplifier, and this is the reference voltage, right? Now, depending on the number of stages, or depending on the resolution what we are looking for, we can have multiple combinations like this. So what you can see on the screen now is the architecture for a 3-bit pipeline ADC, where you can see 3 stages here. This is stage number 1, this is stage number 2, and this is stage number 3. All right. So you will also see that all the blocks like sample and hold and comparators are the main block, and one input of the comparator is always connected to Vref by 2. And to pass the output of the first stage to the second stage, you will have a summer and an amplifier, right? So let us see how this works, and based on that we'll have further discussion. All right. So so since this is 3-bit pipeline ADC, we have 3 stages, and look at the components in every stage. Only in the last stage, since this stage is not passing any information to the next stage, we don't have a summer or a multiplier. Rather, here the direct comparison is done with respect to the Vref by 2. Right. So how we can name this is, since it is a 3-bit ADC, whatever we get as the output of the comparator, output of the comparator is directly the bit conversion for that stage. You can directly consider like that. So this will be D2, which forms the MSB. This will give you D1, and this is D0, which forms the LSB. All right. Now, so what happens is your input signal will be available here, and the input signal will be first given to the sample and hold circuit, and say you are getting some output over here, and let me call this as some Vx voltage, which is the output of sample and hold. That input signal, which is sampled, is directly given to the plus input of the comparator. Now the other input of comparator is actually connected to Vref by 2. That means this comparator is going to perform a comparison between the sampled voltage Vx and this Vref by 2. Right. Now, so that is the first. If you look at the operation, the first step is the sample signal. The sample signal is compared with Vref by 2. Right. Now, the rest of the operation depends on this comparison result, right? So now when you say your the sample signal, in this case it is Vx, when you compare this Vx with Vref by 2, two cases can happen, right? There are two things can happen. One is your Vx can be greater than Vref by 2. The other thing is your Vx, this voltage can be less than Vref by 2. For these two operations, two things should happen, right? So once if your input voltage, which is sampled input voltage, we named it as Vx, if it is greater than Vref by 2, naturally what will happen, since your Vx, the plus input is higher, the comparator will provide a 1 output, right? So the output of the comparator will go high. So this result comparator output as high, or you will get comparator output as 1, right? Now on the other side, if your Vx input is less than Vref by 2, automatically your comparator output will be 0. These are the two things which will happen with respect to the comparator, and automatically that will come as the position, like MSB or whatever position it is, it will directly come there, right? But now depending on this, one more control we have here, that is if your input voltage Vx is greater than Vref by 2, the summer input, so the whatever is coming to the summer, what will happen is one input of summer is Vx, but the other input of summer will be automatically connected to Vref by 2. That means if your Vx is greater than Vref by 2, comparator output will be high. Along with that, this summer will perform an subtraction. What the summer will do is summer will subtract this Vref by 2 voltage from Vx, and then that will, it will be passed to the amplifier, right? So that means here one operation will happen. So what will happen here is, if this is the case, summer subtract Vref by 2 from Vx and then amplifies. This is one case. The other case is if your sampled voltage is less than Vref by 2, then summer will pass the original signal. So how this summer can pass the original information? The other input will be actually given to 0. Then summer pass Vx to the amplifier. This is what will happen in every stage, right? Now we call the output of every stage as residue of that stage itself. Say for example, since this is a 3-bit ADC, how we can name this is, since you have 3 stages here, we will name the output of the residue of the first stage as, say this we called as, this will be called as V3, and the residue of second stage, this will be called as V2. We have two residue output, right? The output of the first stage and output of second stage, V3 and V2, right? So this is a fundamental operation. For a pipeline ADC, there will be, for an n-bit ADC, there will be n stages, and every stage will have a sample and hold circuit, a comparator, summer and an amplifier. And how it works is, your the input signal will be first sampled. Once it is sampled, it will be compared with the help of comparator with the reference voltage of Vref by 2. Based on the comparison result, comparator will directly give you the digital output there, and summer will perform an operation. If your input is greater than Vref by 2, summer will perform an operation by subtracting Vref by 2 and multiply it with 2 and give a residue at the output of that particular stage. If not, if the Vx, if your input is less than Vref by 2, it will be passed as it is, right? So this is how this the working of this, this is how this pipeline ADC works. Now what we'll do is we'll take a specific example, say in the 3-bit ADC itself, and we'll see how this happens for every input input voltage, right? Now when you look at the advantages of this, so one thing you can see that if you want to get an output for a specific input, it has to actually pass through the so many stages, at least initially, right? So even though it is having high throughput, there is an initial latency of at least n clock cycles. Say for example, if you have a 10-bit ADC, you have to wait for 10 clock cycles to get the first output, right? So that initial latency is definitely there, because even though one conversion will be completed per clock cycle. Now one more thing is this actually this architecture works on the residue produced by the first stage. right? So for example, the residue of the first stage is being operated on by the second stage. Now once that is done, say for example, once the first stage produces a residue of V3, the second stage will work on that V3 and will continue. At the same time, the first stage can actually take up the next input signal and it can start processing it. In that way, actually the throughput is high. Alright, so I hope you understood the basic architecture of this pipeline ADC. So what we will do now is we will go ahead and look at specific example of this 3-bit ADC itself and see how we can understand the operation and generate the output voltage. Right. For that I will be taking the same architecture and I will be keeping it here. Alright, so what we do is we'll this is a 3-bit pipeline ADC. 3-bit pipeline ADC. I'll keep reference voltage as say some 5 volt. Right. Now what I will do is I will look for specifically look for conversion process and say I'll take input voltages, different values of input voltages, and we'll look at the residue produced at the output of every stage like V3, V2. And also we look at the digital output D2, D1 and D0, how this is being produced. Alright. So for reference, I'll here also I'll take reference as 5 volt itself. Alright. Now let's look at this conversion process as what I have explained. Let us look at the conversion process, how it happens for some sample input voltages. Say, let me start with the 2 volt input signal. Say the input voltage which is available here is 2. Input is 2 and the sample so what I meant by writing it as 2 is I will write this instead of V, I will write it as Vx for more clarity. Your input voltage, both are I am considering, at least for now I am considering both as same, right? It is 2. If it is 2 volt, what will happen? Now what is my reference voltage here? Reference is 5, so this will be 2.5 volt, right? So what will happen? The voltage coming here is 2, this is 2 and this is 2.5. The meaning is the comparator will directly give you a 0. So D2 will go to 0, right? I can directly write the output here, D2 will be 0. Now if your Vx is less than Vref by 2, the result is the same voltage will be passed here, right? No, there is no subtraction of Vref by 2. So the same 2 volt will come here, 0 will come here. Now 2 and 0 will come and it will be multiplied by 2 and what we get at V3 will be 4. So I can write this as 4 volt. So V3 will be 4. Now again this will be processed by the next stage, right? So V3 will come here as 4. Now 4 will be compared with what I have here is 2.5. Now 4 will be compared with 2.5 and as a result of that what I will get will be D1 will be 1. So I can directly write D1 as 1 here. This will be 1. And since your input is greater than Vref by 2, I need to subtract Vref by 2 from this voltage. That means here the subtraction will be 4 and 2.5, which will result as 1.5 at the output. Now if I have 1.5 here, that will be multiplied by 2 and the residue now will be 3 volt. That means I will get V2 as 3 volt, right? Now if my residue is 3 volt, what will happen at the last stage? 3 will be compared with respect to 2.5 and it will produce an output of 1. So this will be 1. This is how conversion happens in a pipeline ADC. Alright. So the input voltage will be first compared with the comparator and output will be produced here. That will serve as your MSB bit. Now depending on the output, the summer will decide whether Vref by 2 should be subtracted or it should pass the same signal as it is. And after that we have to multiply that with 2 and this process will continue. Alright, let me take one more example. Say if I have 3 volt as the input, what will happen? So if it is 3 volt, what I will get here will be 3. Now that this remains same as 2.5. So if it is 3 and 2.5 will be compared and the output will be 1. You will get 1 here, right? So I can directly write 1 here. Now this is 3, this is 2.5 and since your input is greater than 2.5, what will be subtracted? 2.5 will be subtracted from 3. So the result is 0.5. 0.5 will be multiplied by 2, you will get 1 as V3, so your V3 will be equal to 1 volt. Alright, now V3 is 1, so 1 will come directly, 1 you will get here. Alright, and that 1 voltage will be again compared with 2.5, and you will directly get the result as 0 here, so 0 will come here. Now since it is 0, the 1 will be directly passed, so this also will be 0, so 1 will come here. As a result, you will get 1 at the output. Now that 1 will be multiplied by 2 to produce V2 as a residue, which will be 2 volt here. Right, now 2 will come here, 2 volt will come here, 2 will come here, this is 2.5, this is smaller, so you will get 0 as the output. Your output will be 100. Alright, so in a similar way, for every input voltage, this conversion will happen stage by stage, right? So when you perform the comparison, you should actually write in. So I have done on this figure itself by just changing the colors. It will be more clear if you can write in steps, right? Say for example, your input voltage is say 4.5. What is the first step? What I can write is, since your input voltage Vin is greater than Vref by 2, right, your comparator output, so D2 will be 1. I can directly write 1 here. Now since that is the case, I should subtract 2.5 from this. That will give me a value of 1.5, right? So 4.5 minus 2.5 is 2. I'll get a value of 2 here. 2 will be multiplied by 2 and I'll get 4 volt here. Right, now again 4 is compared with 2.5, again the output is 1 because this will be higher, and then 2.5 will be subtracted from this. So 4 minus 2.5 is another 1.5. 1.5 multiplied by 2 is 3. So I got 2 residues here. 3 will come here, again comparison, I'll get it as 1. So this is how the pipeline ADC works. Alright, so what we have to do is, first you have to look at the number of bits, what the ADC expect. Depending on that, you can actually develop the architecture. And from the architecture, look at how many residues are being produced and how the residues are being utilized by the rest of the stages. Right, and as mentioned, the main advantage is through high throughput. There is an initial latency, but you know that for a specific input voltage, if the first stage operated on that and if I had produced a residue, the rest of the things will be taken care by the rest of the stages, and the first stage is free to actually take up the next voltage or the next input which is available. Alright, so this is all about pipeline ADC. I hope you understood this. You can actually try for different input voltages and just make a comparison table based on that. Alright, thank you so much for listening to this lecture. We'll continue this with the next ADC architecture, which is SAR ADC, in the next video. Thank you.